Welcome everybody. We're in track 6, over the air and in the device. Our next speaker is Matthew Rowley with how many bricks does it take to crack a microcell?
All right, so the slides that are on the CD are not up to date. This link at the bottom has the slides in the white paper. The white paper has a little bit more detail than what I'm going to be talking about, but if anyone wants it, it's right there. It'll also be on the last slide of the presentation. So again, my name is Matthew Rowley. I'm currently a senior security consultant at Montesano. I typically hate when people give backgrounds on themselves before they start their presentation, but I think it's pretty applicable to my talk. It's going to go through a hardware level all the way to software level. However, my background has always been in software. So some of the stuff that I'm going to talk about in a hardware perspective may or may not use the terminology correctly, but just be a forewarning about what I'm going to be talking about. So in terms of agenda, this talk is focusing strictly on the reversing from a hardware perspective all the way up to the software perspective of this specific microcell that I was looking at. It's not focusing on any of the GSM or 3G technology, so I apologize if anyone's here hoping for that. There was good talks last year on that specific case. But I'll start with the device background, then start talking about my battle with the network, the communication that the device actually performs, then the cage, which is actually just the surrounding cover of the device. Then I'll get into the hardware aspects of it, talking about the debug pins on the actual device, going through SPI, JTAG, serial communication that it performs, and then go to the software aspect of it and looking at U-boot, some kernel reversing, firmware extraction, and binary reversing. So first, the background on this specific device. I'm assuming everyone here knows what a microcell is. It's a device that you plug into your internet connection at home and your cell phone connects to it and backhauls all of your cell communication through your network connection. So it will, instead of connecting to a cell tower, will connect to this device. The one in particular I was looking at had a web-based interface that was hosted on the service provider's webpage. There was really no interaction that I could have with the physical device that I had in my hands. The configuration was done on an external webpage and then somehow pushed either to the device or pushed to your phone, which would allow you to connect to it. You had to provision specific phone numbers in that webpage, so not anyone who just comes into my apartment would connect to it. And I think there was a maximum of 15 or 20 that you could actually allow to connect to your device. I started looking at this device because my cell reception was horrible in my apartment, and somehow the service provider proactively sent me a card saying, hey, we noticed a lot of your phone calls are being dropped. Here's a free device if you go to the store and pick it up. At the same time, at this point in time, I was working at Intrepidus Group which focused on mobile security. So those two hand in hand kind of made sense to start looking at this device. Again, like I said before, I've always been a software person. So ShmooCon last year, Stephen Ridley did a talk about hardware for software guys, which kind of also fed into this whole interest in trying to look at the hardware aspect of security. So it was a good learning tool for me. So the first thing that I wanted to look at when reversing this device was network communication. I didn't have to actually do anything physical to it. I connected the device to a server that I had in my apartment, which had 2 NICs, and then just monitored the communication. It doesn't have any wireless functionality in terms of Wi-Fi, so I actually had to physically connect this to a box. But looking at TCP dump, I saw HTTPS traffic, an IPsec tunnel that was initialized, and some multicast stuff, which I kind of just didn't think about. The next step, what I tried was to get man in the middle of the traffic, the HTTPS traffic, with Mallory, which is a software that was written in Intrepidus Group that facilitates all man in the middle communication and manages all the certificates for you. However, it was all mutually authenticated. I couldn't get in the middle of the IPsec tunnel, and the multicast stuff was kind of confusing to me. So in this case, the network beat me on this one. I didn't gain any additional information from the device. Looking at the network communication traffic, it was essentially all encrypted. The next thing I started looking at was physically taking the device apart, or looking at the cage. This is what the device looks like. There are 2 screws on the bottom on the orange panel at the bottom, underneath a piece of tape. You unscrew those, the 2 white, that orange panel can come off. Then on the sides, there's 2 white panels that can come off as well. And then finally, the board is actually connected to the gray part in the middle. So my idea was to unscrew it and just start pulling everything apart and seeing what would happen. After I did that, I tried booting it, and this is what it looks like disassembled. You can see there's four panels. The board would connect in the middle of it. But after trying to boot it again, it didn't turn on. It just sat there with a light flashing. So this is brick number 1 that I had on my hands. However, I called customer support and tried to convince them that I had no idea what was going on. The thing just stopped working. So I ended up, after about 30 minutes of debugging the device with the first tier support, I ended up getting the customer service support people, or the technical support people, and they kept saying that the tamper flag was switched on their server end of things, or on their console that they're looking at. Which, to me, I tried to start pushing buttons and try to dive further into that to see, like, hey, can you just turn the tamper flag off so it works again? And he was like, it doesn't work that way. And they kept asking me if I had dropped the device or if I had pulled it apart at all. And of course I said no. But eventually I ended up pulling a story out saying that the cleaning ladies had come in the day before and they must have done something to it, or it must have fallen off a ledge or something. So in the end, he just said, go to the store and you can replace it for free. We'll just give you a new one. So I went to the store, got a new one, and now it's round 2 against the cage. This time I was a little bit more careful. When I was pulling it apart, I noticed these sets of jumpers that were on the front and the back of the board. So there's 3 jumpers. This is the back of it, but there's these 3 jumpers, and then that gray piece is underneath the jumpers. The jumpers are just like the things that you put in the back of a hard drive to determine if it's a master or slave. But what I didn't notice when I first took this apart was that when the outside white parts of that cage are actually connected with a little clip to that gray part. So when you pull it apart, those jumpers pop off. 2 of the jumpers, or in my case, 2 of the jumpers were fake jumpers, and one of them was actually real. It completed a circuit on these 2 pins that were on there. So what I was thinking that happened is when I turned it on, it checked these jumpers to make sure that they were in the right configuration, and then it would send a signal if they weren't back to the mothership to tell them that someone's messing with this device, you shouldn't let it move forward. So in order to get around this, when I was pulling off the bottom part, I could see like a couple millimeters I had space to slide something in. So I just bought this saw from Home Depot, looks like the one down there, and I started sawing through the clip that was connected to the jumpers. I'd never seen any sort of hardware protection like this before, and I was like, it just didn't make sense to me, and how easy it was to get around. But I mean, obviously they got me the first time. After doing that, sawing those off, the jumper stayed on. Next time I booted it, it worked fine. I was able to dismantle the cage and successfully boot the device on its own, just as a board without anything surrounding it. So in this case, I beat the cage finally. So this is what the board actually looks like. In green, there's the main components that are highlighted. It's kind of, you can see it pretty well. And then in blue and red, there are these sets of debug pins, or what I thought were debug pins that I was going to focus on first from a hardware perspective, because again, I have no ability to communicate with this device, and everything that's happening that I could see was all encrypted. So I had to figure out some way of actually communicating with it. On the left, there's a GPS chip. When you register the device on the web page, it forces you to also give a specific location of where it's going to be working for emergency 911, stuff like that. And then there's a RA-Link in the middle, the GSM portion under that heatsink in the middle bottom, Xilinx chip, that's a black box, and then the Pico chip on the right, which is under another heatsink. So the 4 different sets of debug pins that I'm going to go over are just labeled. I don't know exactly what the letters and numbers mean, but that's how I reference them throughout the rest of the talk. So there's C541, JP1, 2, 5, and 6, PL1, and PL2. So the first set of pins that I was looking at was a CS541, which just were holes in the board that looked like a header had just been pulled off of it, or just not been put into it. And the tool that I used to actually analyze the data that was going over this is called a Soleil logic analyzer. A logic analyzer is a device that you actually plug into, or you connect to these specific hardware pins, and it will sample those pins at specific intervals in time and over a specific amount of time and tell you if it's a 1 or a 0, basically if it's a high voltage or no voltage, and then from there it can analyze that set of data and give you a text representation or a hex representation of what's actually being communicated over these pins. So the workflow that I was going to use in order to determine what data was going on this was first to use a multimeter to make sure that once I do plug my logic analyzer into this, it's not going to blow up. It's not sending a huge high signal that's going to actually cause the thing to fail. From there, I was going to plug the logic analyzer into the pins, start the logic software, which runs on your computer, and then plug the device in. When I think data has been transmitted, stop the logic software, and then try to analyze it with the preset analyzers that they have built into the logic software. This is this is what it looks like when you plug all this stuff in. As you can see, it's very fun to do. This case, it was actually not the pins that I'm looking at now, but on this one I actually had 14 plugged into the logic. So that black box is the actual, at the top of the image is the actual Soleil logic analyzer. That plugs into your computer, and then the other side obviously plugs into the pins on the board. So after I started this and was following my methodology, I see the top, which is a zoomed out version of this. I was sampling at 16 megahertz, which was fairly high for this amount of pins. And the top image is of about 40 seconds of sampling, 35 seconds of sampling. As you can see, there's just these little blips that are happening in there, but when you zoom into it, on the bottom, you'll see that it's just, each one of those blips is up and down, and obviously the bottom means that there's nothing going over that pin, and on the top means that there is something going over that pin. So since there's only one, I was going through all these analyzers and knowing nothing about what any of this is, I eventually end up applying this async serial one to it, which had a thing called auto baud, which automatically determined the baud rate or how fast it should be reading this. And as you can see on the little bubbles above everything, it automatically determined that there was actually data. So it's like you can see that like \r\n on the last part of that. So from there, I was able to export that data into a CSV file, pulled it open into Excel, and then copied and pasted the specific pin that I was looking at into VI, and then did some manipulation so it wasn't one character per line, and this is what I ended up coming out with. As you can see, there's one specific string that shows up commonly through that, and that's a $GPGA2 something something something. Now, after Googling that, I just saw that it was GPS related data. It was, however, the GPS chip was sending its coordinates to some other chip, whatever the receiving chip was. It really didn't interest me at all because my goal is to gain access to the device, and the GPS stuff, whatever. However, reading on some of the forums, people were saying that it would be cool if you could use this device in other countries because then you won't have to roam. But when you try to register it, or when the GPS sends back to home that you're in a different country, the thing stops working. So it's possible, theoretically possible, to pull this chip off, to first log all the data that's being transmitted, pull the chip off, create something else that's just sending like your home address or your home GPS signals in the same format, and you can bring it to another country, for example, and start using your cell phone in that country. I don't know if that's possible, but again, not something that I was really interested in. So in this case, I learned a lot of this async serial protocol and how to actually get data off of these pins. However, it didn't get me any step closer to my goal of actually gaining access to the device. The next set of pins were a little bit more interesting. They looked exactly the same, were labeled JP1, which were right next to one of the RA link chip. I did basically the same workflow that I was talking about before, plugging in Soleil, booting it up, starting the software, and then trying to analyze it. This is the top is the zoomed out version of the JP1 stuff. As you can see, the bottom was what we were looking at before. As you can see, there's just like little blips over time, whereas the JP1, there's this huge blob of data and then nothing. So as you'll see later on, or the next slide, that you can just based on the pattern of the data that's going across specific debug pins, you can kind of infer what's happening. So after pulling all that data out, I got this, what you can see at the bottom. You can actually see it's a Linux boot prompt. You can see at the bottom, it says this is ASCII Linux version 2.6.2.1, and it ended up going all the way down to a login prompt. So I was really excited here. So that eventually got me to a login prompt, and this is going to be the focus of the software side of the talk. So I'm going to skip over going further down into this and go to the next set of pins. But in this case, I feel like I won this battle, or this round. The next set of pins I looked at were JP2, 5, and 6. However, there was actually no data being transmitted over them that I could see. The Soleil logic analyzer didn't show me anything. So that round was a draw. There was no show. They didn't give me any information. The next set of pins I looked at were this PL2, which is as you can see, my soldering skills are subpar, but I was able, there's 2 lines of 7 pads on this device, or on this set of pins, and I ended up soldering wires onto it in order to connect these gator clips from the Soleil logic analyzer. And obviously use the same methodology as before, booting the device, starting the software. And this time I saw this, which was actually a lot different than what was seen before. The 3 pins were actually transmitting data out of these 14 pins, when before it was only 1. So at ShmooCon last year, I met Travis Goodspeed, and I know he was really good at hardware reversing. So I sent him this. I was like, have you ever seen this before? Do you have any clue what type of data this is? And he said, it's definitely SPI data, but started giving me some pointers. So I started researching SPI. And without getting into too much detail of what SPI is, it's just another communication protocol like the async serial protocol, and the logic analyzer has an analyzer to decode this data. So these points are the key things to understanding on how you would be able to decode that data that I saw on these wires. First is that SPI has the ability to transmit data up to 100 megahertz in speed. So the first thing I had to do was increase the speed of my logic analyzer sample rate. The actual hardware has limitations on how fast it can actually sample things, but you can configure the software to sample things quicker with less pins being connected to it. Since I only had 3 pins, I was able to sample at 50 megahertz. So I had to accept a risk that it's possible that the data that I was getting is not going to be anything because I wasn't able to sample fast enough. Next is that SPI communicates in a master-slave mode, and there's the ability to have multiple slaves. So you can actually have multiple chips communicating over one specific debug pad output. There's 4 lines in SPI, the MOSI, which is master output, slave input. I always look at things from the perspective of the master, so I just call that output. Master input, slave output, which is the input to the master. And then there's an enable or slave select line, which will basically determine what slave you're communicating with when you're actually sending data or retrieving data. And finally, there's a clock pin. And so in the async serial, the clock was at that specific baud rate. That's when it knew when to sample things. With SPI, the clock is not like a metronome clock. It works in one of 2 different variations. When the clock pin goes from high to low, it will sample the other 2 pins, the output or the input, or vice versa. When the clock goes from low to high, it'll sample the other 2 pins and so at that point in time, when the clock pin changes, what are the output and the input pins at either a 1 or a 0 or a high or a low? After reading all this and understanding more about SPI, you can see zoomed in, you can tell that brown number 1 is the clock pin, and it's going at 16 different up and downs through each blob. Then the next one was the master output, and the following one was the master input. However, so this, again, you can see the bubbles representing the data that's above them. And this specific configuration, I had it at 8 bits per character, or per, I guess, character, which is the default. However, it could be 16. I kind of spent way too much time trying to analyze that data and gave up. I could see that there was data going by, but still to this day, I don't even know what that is. So in this case, the debug pins beat me. So then I started moving forward to another set of debug pins which looked exactly the same as the last one, just in a different location on the board, which was PL1. There was no data like the other pins being seen over this. However, someone at Matasano told me that these scream JTAG. They look like they should be JTAG pinouts for whatever reason. It was actually Cody who did a talk on Tuesday. So I started reading about JTAG, trying to figure out what I could do to get some sort of data or some sort of anything from these pins. Before doing this, the only thing that I knew about JTAG was that I used this in cable modems before at a previous job to pull and push firmware. So my hopes were that I was going to be able to do this to one of the other chips on the device. And I knew that it was some sort of standard that developers use to debug chips after a board has already been made. So again, after reading a lot about JTAG, without going into too much detail, these are the set of points that I needed to understand in order to communicate with this chip. First is that I wasn't seeing any data because JTAG pins on their own don't transmit any data. The clock is actually outside of the JTAG ports, and that's what actually will determine if pins should be transmitting or receiving data. So you need a specific external cable. You can't just plug in the Slay logic analyzer because something else needs to be triggering this clock up and down. So then from there's 5 pins that need to be connected: the VREF, TMS, TCK, TDO, and TDI, which I ended up figuring out what they actually meant, but at the time I was looking at pinouts and then plugging it into, oh, this is TMS, oh, that should be TMS. But there's 14 pins on these pads, so how do I know, my problem was, how do I know which 5 pins should I be plugging in? The next is that, like SPI, there can be multiple devices plugged into one JTAG pinout, which is called, they're called that, and if there are multiple devices, multiple chips connected to one pinout, they're daisy chained together. That's the terminology that they use. And then finally, that each chip that's connected to this daisy chain is called a tap, which is going to be important when configuring the software. So first thing I had to do was find a JTAG cable that I could use. I ended up purchasing this Olimex ARM USB, which had serial and USB capabilities. I bought it on a whim just because it was $50. And then I used OpenOCD software. It was open source, and it supports the cable that I had purchased already. And the key point was that it had the ability to auto-discover taps. I didn't have to configure anything. It would attempt to auto-determine if there's any JTAG chips that are communicating on these pads. And reading through the documentation, 2 key points stood out. Was one, that it can reliably determine the tap ID, but unreliably determine the IR len, which is instruction register length, which I'll talk about later. So the methodology that I was using in order to try to determine what pins should be plugged into where was just Google searching common JTAG pinouts that had 2 sets of had 14 pins and 2 sets of 7 rows, whatever. So the first thing, if there's any data coming out of any of these pins, it's definitely not JTAG, because I know that JTAG doesn't transmit any data without an external clock. Then I would try this common pinout and then flip the thing 180 degrees and then try it again, power on the device, and then start this OpenOCD software to see if it can auto-discover a specific tap on the device, or any taps. So do you guys remember these these games that are games, quote unquote games, that are sitting in doctor's offices? Well, this is how I felt trying to plug these things in between the cable and the board. For some reason, I could not wrap my head around how to get, I don't know, whatever. Anyways, once I finally completed that game and I got the pinouts correct, I started the OpenOCD software, and as you can see in the yellow, it said that it auto-discovered a tap, and it gives it a specific expected ID, which is some random number that I have no idea what I'm doing right now. And then the instruction length said 2, and then there's an error. So I started using that ID in Google search, that expected ID, and it turns out that that ID matched exactly to the Xilinx chip that was near that set of pinouts, to the model number that was on that chip. So the next step was to configure the OpenOCD software to communicate with that chip. And there's four different things that you need in order to do that. First is the expected ID, which it already gave me. Then the IR length, the IR capture, and the IR mask, which I originally just started throwing some numbers at it and seeing what it did. Everything was turning out to be an error. And then I started reading about another concept that's kind of hand in hand with JTAG, which is BSDL, which is just a configuration file that tells a developer how you can communicate over JTAG to a specific chip. The JTAG is a very loose protocol. There's minimal that's required for it to be implemented, and developers or the chip manufacturers implement all these additional functionalities that is not necessarily public knowledge. But fortunately for me, the Xilinx people allow you to download it for free, this BSDL file, with just signing up on their webpage. And I saw in this file there's these two things that I needed to configure the tap. The instruction length and the instruction capture, which the instruction length is 6 and the instruction capture is XXXX01. So modified my configuration file to add that tap in there, and this time I booted up, or I started the OpenOCD software, and there's no errors, which I thought one step further. This is awesome. Next thing I did was, so OpenOCD works in a client-server mode where when you're starting OpenOCD, it opens up a port that you can telnet to, and then another port that you can connect via GDB and send commands to. So the first thing I did was sent this command JTAG init, which again didn't throw any errors. It gave me the specific tap that it found, the manufacturer number, the part number, and the version number. And so I'm like, yes, I'm on the right path. However, if I would have thought about this before taking all the time of understanding JTAG, I would have realized that the only thing that I'm going to be able to communicate with is the Xilinx FPGA, and that's got no flash, no operating system, and the only thing that I may be able to do is reprogram it. So again, it's kind of a fail on my part, but not because it was just because I simply didn't think. I was getting excited and being impatient. So in this case, I feel like the debug pins beat me out here. I learned a lot about JTAG, and however, again, no closer to my goal of actually gaining access to the device. So switching gears now to the software level, I looked at all of the pins, and the only one that I had any sort of path to gaining access to the device was the JP1 set of pins that ended up bringing me to a Linux boot prompt. So I bought this 3v3 USB FTDI cable that allowed me just to connect through a screen terminal session at a specific baud rate, and I was able to interact with the device. What I was doing though when powering on the device was I was plugging in the device, then starting the terminal session, and so I was missing the whole beginning part of the boot procedure, and I was just getting to this login prompt. I was like, what? How? I tried guessing, obviously root didn't work, but after a while I ended up keeping the terminal session open and then powering on the device, and I noticed this. The beginning of U-boot and it paused for like 2 seconds that you wouldn't really notice, but after booting it about 50 times, you could actually see this. And number 4, and this is actually how it's spelled on the device, it's not a typo, enter boot command line interface. So next time I powered it on, I continuously pressed 4, and it dropped me into this bootloader interface. A U-boot bootloader interface, and me not knowing much of anything about bootloaders, started reading once again, and there's a help command that showed me the available commands that I have on this specific device. And after enumerating all the commands that were available, the only thing that was really going to be helpful to me was this MD command, which is memory display. So there's a flash chip that is somehow connected, and I can read data off of that. So my idea was to use that to dump data, log it using screen, and then create a Ruby script that transfers that data into a binary file. Now, thankfully, when Googling around on specifics for this device, there was an exploitworkshop.org. I don't even think the webpage is up anymore, but they gave me this memory layout of the specific device. It actually wasn't even up when I found it. I saved the file locally from a Google cache page. But as you can see, there's a 4 megabyte flash memory address location, so BFC through C00. That was my goal. That was what I wanted to start pulling off and start trying to analyze, because as you can see in the bottom, there's U-boot image, Linux kernel image, and some extras. So I know this is booting Linux, and it looks like Linux is on this portion of memory somewhere, so my goal was to try to use that to my advantage. So the memory display command literally just outputs it straight to the screen like a hex editor would. So I had to write a script that took into account endianness and took into account specific memory address locations, and was able to dump this and then turn it into a file, and then that file was nothing. It was just a set of data after running file in the command. However, reading a bunch of blogs, this is like a common path that people go down when trying to reverse firmware images. So the next thing I wanted to look at was what can I gain from this big blob of data, this 4 megabyte flash set of data that I have sitting in front of me. And doing this, there's 3 tools that always, it was a common workflow with these 3 tools. The first one is strings, and the second one is file, which I'm assuming everyone knows. And the last one was this tool, I don't know who wrote it, but it's called binwalk. And what it does is it steps through a file, and each specific byte in that file, it will essentially run the file command from that byte onto the end of the file. It doesn't actually run the file command, it has its own implementation, but that's essentially what it does to see if there's a file located within some big blob of data. So the first thing that I did was this with the full 4 megabyte flash was a run file, and it didn't give me anything. Strings didn't give me anything either. However, when running the bin dump? Yeah, bin dump on it, you can see that representation at the bottom. There's a bunch of LZMA partitions and 2 Umage Linux images, which directly related back to that exploit workshop thing that I was looking at, the memory address layout. So the first thing that I did was pull all those LZMA partitions out using DD, and then tried to un-LZMA them. The only one that actually successfully decompressed was this last one, which I call LZMA4. Running file on that just says another set of data. However, running strings on it gave me one step closer, and it's showing actual real strings and data that's in this file. Again, the next thing that I ran was binwalk, and I see a ton of LZMA partitions, or I call them partitions, parts of this file and some squash file system images. When reading this, when doing this, I was reading a blog post about someone reversing a router firmware, and they were explaining a trick of they found a squash file system partition that existed within a file, and they were able to modify the header to successfully unsquash that file system. So that's where I originally started focusing. Everything failed. I spent a couple days trying to get that working. However, if I would have just read this, once again, I was too excited, trying to move too quickly. You can see all the created dates on this are way in the future, which to me makes me think that that's definitely not anything of use. It's a false positive of the binwalk tool. So the next thing that I did was pulled out every single one of those LZMA partitions manually, and again, the last one was the only one that decompressed. So I call this 4.18 because it's the 18th partition that was in that file. Running file on it says something ASCII. I just said I saw ASCII and kept moving forward. Running strings on it showed me this specific format of the file where it looked like there's some ID number, then an executable, and then possibly the contents of that executable. And running binwalk on it showed a ton of binaries, some more LZMA stuff, but I felt like I was on the right path. So after Googling around a little bit, I determined that this was actually a CPIO archive based on the format of the file. However, if I would have just read, again, the file command, it told me exactly what this was. So that was a waste of a couple of days, but now I know how to move forward. So running CPIO, I could see a list of files, which, however, CPIO has a limitation on it when it comes to extracting files from the archive. They go to their exact location. There's no way of putting it into like a reference directory. There's no way of actually of giving it a root directory of where it should place all these files. It just places them, like if it's Etsy password, it will place it on Etsy password on your machine. However, there was a nice little flag called -r, which will allow me to interactively rename all 208 of these files. And I did that manually as well. That was awesome. And yes, after doing all this, weeks later, people are like, you could have done that a lot easier. I was like, yeah, I know. was too excited. I wanted to keep going. So the next thing, so I've got all these files now in a directory, and it's a boot file system. So I wanted to try to start reversing them. Again, my goal is to gain access to this device, and all I have is up to a Linux boot prompt or a Linux login prompt. So I started reversing the applications that were in here, and there was three main focuses of the reversing. First were these scripts that were in the sbin directory, which were part of the boot procedure, and then I could relate the strings that were being printed out from there to the strings that existed in the scripts. And then I also found that a lot of these binaries were using eval, which you'll see later it directly relates to the boot procedure and these scripts. So on kind of a side note, within that memory address layout, there was also something that was defined as picoconfig, which had basically a configuration that could be read from the bootloader that had a few things of interest in there. One was tamper-proof, which was a binary representation of the plugs that were on the front and the back of the board. So presumably I can pull those out, overwrite tamper-proof to all zeros, and the device should still work. I'm not sure if it's random for each new device or what, but there's also the ability to put it in a learn mode, and again, would presumably learn what the pin configuration is. There's also a node in there that shows, so the picoconfig is just like a key value pair in a tree. I'll show you what it looks like next slide, but there's also what looked like specifying a firmware image on a TFTP server at some 192.168 address, which was confusing to me because how was it getting to that IP address? And then the last part was that there's a firewall node that directly resembled exactly what I was seeing upon boot. Now, this is what the top part of this slide is the picoconfig, and specifically the firewall portion of it. As you can see, the port protocol and the destination IP address are directly related to what's happening this IP tables command. So again, I don't have access to this device, and I was thinking if somehow I can override that and run a command, I may be able to do some sort of command injection to get access to this device. It turns out, looking at one of the executables that's reading this memory address location and reading the configuration file and calling these eval functions, it's actually calling eval sh-c and then whatever IP table string that it determines from that memory address. And as you can see on the top one, the comment, it's actually, you can see it's a format string, so there's a %s in there. So my idea was that if I can somehow override the IP address to run some sort of command, I may be able to gain access to this device. The first test of what I was just trying to do is ping something, or do an echo of just seeing if I can get some sort of output. So going back to U-boot, not only was able to read the memory on the flash chip, I was also able to write the memory. However, any attempt that I was trying to do to modify this picoconfig portion of memory was failing. Nothing was working. I would write to it and then read the exact same bit back, and it just wouldn't change. I had no idea what was going on. Then I noticed this thing called protect, one of the commands. Specifically there's a print environmental variables, which is a set of environmental variables and commands. So I saw this command u_b, and the first thing it says was protect off. I was like, awesome, let's run it. Bad idea. If you actually continue to read the command, it proceeds to erase the entire flash chip as well. So I now had a second brick on my hand. Again, called up customer service and said, I don't know what happened. Again, 30 minutes of debugging. This time they didn't say anything about a tamper flag, but they kept asking me if there was a power surge in my apartment, because there's only one light that was just solid, which I assume means that you have a brick. And I made up some stories like, yeah, there was a storm last night. It probably was that. Anyways, I couldn't totally convince them that I didn't know what was going on, and it was like 2 hours wasted of my day, so I ended up hanging up with them. And I know from the last call that they take notes about everything that you're talking about. So what I did was just went to the store and said the same story as before. Yeah, I talked to the people at customer service. They said I could just come in and replace it. Ladies were like, all right, let me look up the notes. And she just like read the first few sentences. She was like, all right, perfect, here we go. However, The only, the only problem was that they didn't have any in stock, so I had to wait. They had to get one shipped to me. Now, while doing this, I remember looking at one of the bin dumps before, and there was a Linux kernel image in there. So I wanted to start focusing on anything else I possibly could while I'm waiting for this device. Now, also while doing this, I sent Etsy password. I tried to crack it with John the Ripper. It was in this really weird format I had never seen before, which was, it was just a 13-character string where the hash is supposed to be. Someone explained to me what it was before, some old school hashing mechanism. So I really didn't have any faith because I didn't think this was a legitimate Etsy password file. I thought it was somehow dynamically being generated when the device boots up. So I sent that. It was just running in the background on one of my servers at home, and then I moved forward to looking at this Linux kernel image. That's the binned up output, as you can see, image type OS kernel image. I found out based on some of the other information that was being used or that was being displayed upon boot that this is the specific configuration that you needed to load it in IDA. The start address is 8. The RAM size is essentially the size of the file. And then from there, you'd have to go to the specific address location that it starts running instructions from and have IDA start analyzing it. So after doing that, I got to a place where I have all these functions, which is what's shown on the left, but none of them are named. They're just, I mean, I'm one step closer, but it doesn't really give me much. I'm not going to go through and analyze every single kernel level function that exists in this huge firmware image. But I did also notice that on the right-hand screenshot, in the strings portion of IDA, there's what looks like to be function names somewhere in this image, or in this, in the image that I loaded. So when I started looking at it, specifically I was looking at the memcopy string that's in there. I noticed, if you can see on the left-hand side, the highlighted address location of the beginning of where literally the string memcopy starts. I used IDA to search to see if that byte that set of bytes existed anywhere else in the image. Turns out in only one other place it existed, which is, as you can see highlighted on the right, the actual byte value is, if you go from the bottom up, 8027CDE8, which directly is the exact thing on the left. I thought that this couldn't just be a coincidence, so I kept looking further. And after it was also, the next set of bytes was the exact start of one of the functions. So I kind of made an assumption that it's either a function and a function and then a string, or the string and then the function, in some of that order. So I ended up writing a Ruby script that pulled out all these memory address locations from the file and created an IDA script that would load these memory address locations, or load the string literals into IDA and point them to specific memory address locations. After doing that, I got a partial representation of what the kernel functions look like. But while doing this, I got an email from Corey Benninger. He works at Intrepidus Group, and he pointed me to this GPL portion of the pamphlet that they give you with the device. And it basically says, there's a bunch of GPL software in here. If you want copies of it, send $9.99 for shipping and handling to this specific address. Oh, and by the way, if you have any questions, you can email us here. So I sent an email to them saying, I don't want to send you $9.99. Will you just send me the files? And I just waited. While doing this, I still didn't have the device yet back from the, I almost slipped, from the company that I was using. Fortunately, John the Ripper succeeded. After 7 days, the root SSH and SSHD passwords both cracked with the same passwords. It ended up being 7 characters, all lowercase. So now I know that when I get this device, I'd have root on it. So I was really excited. Before I got the device, I also got an email back from the company, and they sent me 2 files, or they sent me links to 2 files. The first one was this DPH151, which was the full boot chain for the operating system that I'm looking at. Literally a tutorial on how to build a firmware image on Ubuntu for this device. And then this other IP access AP, which is some of the open source software for another chip that's on this device. Now, when I actually got the device back, I was able to log in and start playing around and understanding more of exactly what this was doing. And what happens when the device boots, it sends a GPIO signal to another processor, which they refer to as Pico, that causes that chip to boot. That sends a DHCP request back to the chip that I am actually in, which they refer to as the router. And it requests an IP address from this /30 address. Then it configures IP tables to forward a specific set of ports to that private IP address. So within that piece of hardware, it's already NATing inside of itself somehow. None of those ports were open that were being forwarded to the second processor, but it uses IP tables to do that. So presumably they should be open at some point. Another thing was there's IP server service running, which allowed for inter-process communication between the Pico processor and the router processor to ask for things internally like uptime and has this been tampered with and whatnot. Then there's a wizard service that was running that allowed for remote commands from over multicast from third parties. So somehow the company was able to had the ability to perform actions on my device through this wizard function. The last one I looked at was the CFG_flash, which after looking at it, there was this thing called config flash dash. So it's -S for save, -N for the name, which is backdoor, and -V for one, which after booting that, after sending that command and booting the device up, it binds telnet to 0.0.0. So now I don't need to actually plug in a physical cable to this device anymore. I have access to it just through telnetting of whatever IP address it requests from my router. Now, the Fail Overflow a couple months ago did a blog post on this device and noted that within that wizard application, there was a backdoor packet command line which allows someone to send raw commands that are literally executed with eval just straight up. And it's obviously intended functionality. The developers meant to do this. However, now that it's public knowledge, I'm assuming that they're going to maybe take it out in the next version. So I started looking further because in order to gain access to this device, the first time I still need to plug in, I still physically need to plug into the device in order to run that backdoor command. So I wanted to be able to get a device, plug it in, and not have to run anything in order to gain access to it. So I found this other backdoor packet load serial number function that it calls. And remember the command injection with the IP table stuff? Well, it turns out it exists here as well. See, it calls this CS client set serial number and %s, which comes from the packet that's being sent. So if you just use backticks or $ parenthesis, you can, and then it calls eval sh. So it basically calls sh-c this specific command. So you could use this to send one packet to the device to start the backdoor, unplug the device, plug it back in, and the next time it boots up, you're going to have telnet bound to its public IP address or its local IP address. So that's it. I feel like I completely destroyed this device, and I was able to gain access to it physically and able to get root, and then also have a soft rooting device of it, soft rooting functionality of it, so I don't even need to pull it apart anymore. So to answer the question, how many bricks did it take? It only took 2. I was hoping there was going to be more, but I didn't actually have to pay for any of them, which is good. I wanted to give some thanks out to Raj Umudas, Jeremy Ahn, Corey Benninger of Intrepidus Group, and they helped me a lot throughout this project. Kurt Rosenfeld and Andrew Zonenberg, and then finally Travis Goodspeed. That's it. Again, the slides and white paper are located on the IP address at the bottom. They'll also be on the Modasana research page at some point. My name, my email, and my Twitter. So does anybody have any questions? All right, well, thank you guys. No, wait. Unfortunately, the router, so the question was, I got access to the device, am I going to do, was I able to do anything useful? The router portion of the device, which is what I talked about here, no, there's nothing useful that can happen in it. However, The Pico portion is where all the fun stuff happens, which I've also been able to gain access to, however, not enough time to talk about it in this presentation. Anything else? All right, thanks again.